Hi-oh, here we go again. A little bit about light, shadows, eclipses, and polarization. First off, light itself is what's called an electromagnetic wave. Think about that for a moment. We've talked about in the past electromagnetism. We talked about electrical charge producing a magnetic field and vice versa. That's what light is. Realize all electromagnetic waves travel at the same speed, about 300,000 kilometers per second or 300 million meters per second. That's really, really fast. Take a look very carefully at what's called the EM spectrum, electromagnetic spectrum. Look at the names that we give to that spectrum. Realize all of this is light, every last bit of it. We just give parts of the spectrum a name so we have some reference to which part of the spectrum we're talking about. We have radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. The big confusion for most is radio waves. Radio waves tend to confuse people because they think of sound. Light is not sound. This is just a name given to that part of the spectrum. Why do we call that part radio? Because this is the part that we transmit radio waves on to your radio. Your radio then converts it to a vibration, which is sound. You can see what happens. The size of the wave changes as we go towards gamma rays. They have smaller wavelengths, and because they're smaller wavelengths, there's that large frequency. They're all traveling at the same speed. Remember, velocity, the speed of light, is the wavelength times the frequency. This doesn't change. So if the frequency increases, the wavelength has to decrease. Also notice higher energy as we get towards these gamma rays. As we go that direction, what happens is this stuff can penetrate you. Ultraviolet rays, for example, can penetrate your skin. That's why you get skin cancer. X-rays can penetrate your bone. Gamma rays penetrate all the way through your bone, your marrow, so forth. When we talk about light, certain things are transparent to light and other things are opaque. The word transparent means it goes through. Basically, the atomic structure of a substance takes the light and re-emits it. But when something is opaque, it blocks it. It absorbs that light. Doesn't let it pass through. From here, it leads us to the idea of shadows. Everyone knows that when you create a shadow, you're blocking the light. But did you know there's two parts of a shadow? One is called the umbra. It's that really, really dark part. And the other is called the penumbra, which it looks like some light is getting into. It's not completely dark, and that's exactly what happens. Light bends, and some of the light enters that darker shadow, making it a half-lit, half-dark shadow. A good example of this might be seen when you view an eclipse. If you have a partial eclipse, you're located in the penumbra. If you have a total eclipse, you are located in the umbra. Just to keep it straight, a lunar eclipse, lunar means moon, eclipse blocked out, the moon is blocked out. It turns out with a lunar eclipse, the moon doesn't disappear because some of the light bends around the earth and strikes the moon. So you still see the moon. Unlike the sun, which is completely blocked out, at least the main disk, I should say. So the solar eclipse would be the sun blocked out. Here's some examples you can see in this upper picture, the umbra versus the penumbra. Light itself vibrates. As we've shown at the very beginning of this, it acts as a wave, and we've discussed that in other podcasts. If we could set up some type of gate to prevent waves from coming in through the gate, unless they come in at a specific direction, we would what is called polarize that light. So light that comes in horizontally, we say is horizontally polarized. And if it comes in vertically, it's vertically polarized. When light strikes the road, for example, it hits the road and bounces off. That light is actually horizontally polarized, much like skipping a stone off the water. If you want to block that type of glare, you wear a filter, what's called a polarized lens, that prevents the horizontal stuff from coming through. So if you want to block horizontal, you need to wear a vertically polarized lens. Turns out when you take a horizontally polarized lens and a vertically polarized lens and put them together, you end up blocking the light. Actually, a little bit of violet gets through because it's a very small wavelength. It can fit through just a little bit of it. So here's your glare. Go to the store, buy yourself a $10 pair of polarized sunglasses, and you will never buy another type of sunglass again. Again, if you want to get rid of that horizontal polarized light, that horizontally reflected light, you need to wear a vertically polarized lens. Example here, the bottom right hand corner, you can see some glare here of the sun. It's not over here. You can see the glare. You can actually see into the windshield over here if you're wearing a polarized filter. Hard to see it over here. It gets rid of all that extra glare. Notice, again, look with the sunglasses how they're polarized. They're vertical. They're blocking the horizontal rays. 3D happens, you have depth perception. It happens because you see two different views. Each eye sees its own different picture. So to make 3D movies, you have to make it so each eye sees its own image. So the older technology was that one eye, I should say, has a vertical polarized filter, only allowing vertical light in, and the other horizontal, only allowing horizontally polarized light in. And there would be two images projected onto a screen, so each eye sees a different image. Those images would be slightly offset from each other, giving you a sense of depth. Lastly, let's see if we can apply this knowledge. Non-polarized light, so in other words, it's going in every direction, hits a horizontally polarized filter. Only the horizontal is going to come through. And it turns out, if you remember, if we want to block out the light completely, you would need vertically polarized filter. But we don't have that. We have diagonal, which means some of the light's going to get through. And we really didn't discuss why, but it has to do with vector addition. So what we have coming out of here is a little bit much darker diagonally polarized light.